Swayam Prabha. Digital India. Educated India.
Okay, let's get started. So, we're going to talk about diagram and theory. Okay, basic, let's say, motivation for this is that previous lecture, as you would have, some of you have pointed out to me, that it's kind of complicated in terms of this response functions themselves, and also kind of lacks physical intuition. It's kind of very difficult to follow. So, and this becomes even more complicated as combinations of different kinds of interaction, different kind of correlation functions will kind of blow out of proportion. If I have, for example, multiple field interactions and multi-level systems, kind of multiple, and you can't keep writing down all these expressions. You can. It will take, I don't know, for every small system, it will take 20 pages, which is not meaningful. So, instead, we will come up with a solution, sort of a mathematical tool, where we will be able to write down each correlation function in the form of a diagram. So, what you will see is that with this diagram, we will be able to write down all the correlation functions, not as mathematical expressions, with a lot of nested operators, but rather simple diagrams. And we'll be able to evaluate, okay, for this particular experiment, these are all my set of diagrams. And so you'll have all your correlation functions right in there. And there are tools which use these diagrams. In fact, hopefully this kind of do a bit of QTIP, QTPy simulations. And there, somebody has already implemented all these diagrams. So we'll be able to say, okay, invoke this diagram, calculate response function. Fairly simple way. Alright, so the point is this. At the heart of it is the time evolution of your density matrix. Okay. It's time evolution of the density matrix. Right? There are repeated interactions at given instance in time. And that's what we need to capture. And the interactions can happen or can be induced either on the ket side or the brass side of the density matrix. It's a very important thing. If you have not gotten the physical intuition of this, go back to the previous lecture. Even if you have not gotten any physical intuition, you can take it from me that like matter interaction, I have a field interaction. The field can act either on the brass side or the ket side of my density matrix. Okay. There are some implications for that. We will go into that. So there are field interactions, but there could also be some waiting time afterwards. Field interact, and there is an evolution. And this evolution is always under the Hamiltonian of your system in the back, without the light, because there is no light when it's happening. Right? That's what we want to kind of go ahead. So there are two ways of doing this. One is called double-sided Feynman diagrams. Double-sided Feynman. The other is called ladder. So how do you construct a double-sided Feynman diagram? First thing, draw two lines parallel. Basically, these represent your ket and brass side of your density matrix. For example, two-level system A and B or C, whatever it is. Draw A start with the ground state population. Okay. Now, always the Feynman diagram kind of goes upwards. Okay. Now I want to have a field interaction. Now my field interaction is represented by an arrow. Say this is my C1. Time 0. The field interaction. If I am acting on the ket side, I will raise only the ket side. Makes sense, right? So if I am acting on this, let's say I have another state B, I raise the ket side, keeping the bra side the same. There is some evolution here of this coherence. This sometime it's called, that is captured by our super operator. And after some point, let's say I come with another field. Let's say in this case, I'm now acting from the bra side. And then I'll raise the bra side of my density matrix. So this will remain B. Let's say this will go to C. I don't know for now. Two-field interaction. And let's say that also evolves. And that evolution is given by G of tau 2, for example. It's my super operator, which is telling me the evolution under the Hamiltonian of the system. After some point, and after this evolution, let's say I don't have any more field interactions, then what happens? I create a polarization, this polarization is emitted, right? So that is captured in the diagram. So this would be of course, when it emits, this will come down. Let's say it comes down to some A. How do I capture this in the ladder diagram? The same way I can capture this in the ladder diagram. I have 3 states. Kind of say my first field interaction takes me to A to B. That's my first interaction. My second interaction takes me from B to C. Now, a bit complicated diagram. Don't worry about this because I'm going to use it in a different context. And then finally, you will see polarization coming from. Oh, sorry. Polarization that is emitted to these segments. We are creating AA, generating this coherence, then generating this coherence, and you're measuring that coherence. That is what it is. You're not caring about the final part because it doesn't. So for the sake of this lecture series, let's not worry so much about ladder. Let's focus on double-sided Feynman diagram. So for each light-matter interaction represented in the diagram, there is an understanding on how
this action contributes to the response function. That's a very important thing. So dipole can act either on the bra side or on the ket side. It has some interaction amplitude. In some cases, orientation as well. U dot E, right? That's always important. U dot is an orientation. We'll not talk about that. And here it's mostly absorption, but I can also have an emission effect. For example, I could have a Feynman diagram where I go A, have a field interaction. This will raise this guy, B, A, and I could have, instead of absorption, stimulated emission. Basically, a field coming out this way is referred to as stimulated emission. It will go back to AA. This is also a possibility. Hope everybody can see this. Maybe it's small, but you can kind of see this is simple one field interaction, a two-level system, and what you can see is that if I have an absorption event happening and acting in this direction, it's going towards the arrow and raising. So if I have an absorption, of course you will raise the brow, the ket, on. We'll come back to this later. If you have stimulated emission, the field will be a complex conjugate of the previous field. We'll show that too, and then you will lower. Okay. You could also act on the ket side or the bra side. Okay. Good. Typically, the ladder diagram, if you're acting on the ket side, and the ladder diagram, you're representing this as a solid line, acting on the bra side, and you're showing in the dotted line. And always signal emission should always happen on the ket side. That's a convention. Always coming on the, and it's the last thing after all the field interactions are done, then you will emit the signal. Some basics. We come back to this, we kind of go into deeper into the contribution, the direction to signal, wave vector, but get a feel of how we can represent Feynman diagram. So let's write down some rules for Feynman diagrams. Rules for Feynman diagrams. Rules. Time always running from bottom. To top. Draw Feynman diagram, the time is going like this. Interactions are represented by arrows. What I mean by that, if I have an interaction like this, only the final emission is given squiggly arrow. Remember that these diagrams correspond to specific correlation functions. If you kind of go back in correlation function, there is I over H cross I over over h cross power n, so nth order kind of intrinsically there. A good thing to remember, a convention, is that each diagram has a sign associated with it. Remember, sign is given by -1 over n, where n is a number of interactions, but only from the right side. Basically, whatever is in this zone. I have this, and I have one, and I have something like that, and it's two, so on and so forth. So it's only on the right side. Number of interactions on the right side. Number 4. This is important. Let's say I have an interaction which is acting like this. Left towards right. In this case, my electric field corresponds to e power minus I omega t plus I a dot r plus k direction. If I had, on the other hand, an interaction coming from this direction, my electric field is e power plus I omega t minus I a dot r minus k. Critical points. Of course, given for granted is the emitted light has to have, so this will ensure that emitted light, which is always coming on the get side, has a frequency and wave vector consistent with energy and phase matching, energy conservation and phase matching. If you think about it, these two fields basically combine to give your cosine wave, right? Fifth rule, which we already spoken about. If I have something like this corresponds to excitation. If I have, on the other hand, something like this, and that will correspond to de-excitation. Let's say this is absorption, stimulated. Okay, these 5 are pretty much important rules when you are constructing Feynman, double-sided Feynman. These rules didn't randomly come up. They come from the expressions that we have seen. But thankfully, Shaw, Samuel, and others have compiled these rules based on this, so we kind of, these are strict rules and we construct. Okay. Everybody's fine with this? Let's try to use this to construct linear second order and third order response now, entirely using Feynman diagrams. Hopefully by then, more hang of how to build. Okay, all good. Okay, so linear spectra, diagrammatic approach to linear absorption. Recall the C of t, the correlation function which is there, is trace mu of t, mu of 0, or you can also write this as trace mu super operator g of t, mu It's a correlation function. Let's consider, for the sake of this discussion, two-level system with initial state 0, 0, 0. So in the simple picture, that goes here. There is some weighting here. And then there is over to right double-sided Feynman diagram. Start with 0, 0. And then you come with an electric field. So this, because I am drawing it from the get side, my E1 will have less A1, right? Or your E1 some E1 e power minus I over t plus I K1 dot R. That will be the form. That's because I'm choosing this, right? So once I have this, I will have 1, 0. It evolves till some time, and then this linear response, only single field interaction. You create this coherence, right? And then this will emit your field, collapsing the coherence back to the ground state. So what are the 4 things that happen? You have first excitation. Okay. Sorry, first let's start with this. Number 1 is you are in the ground state. That's captured by this. The fact that you're starting from 0, 0. That is point number 1. Point number 2 is that you're coming with a field and you're raising and generating this coherence. That is number 2. Number 3 is this system evolution happening in this time scale. And number 4 is the emission after a certain time. Free induction decay, which we have already seen. Okay, if my electric field is this, then it's kind of reasonable to assume, consider the polarization is also going to look something like this. And by phase matching, momentum conservation, energy conservation, omega 1 should be equal to omega signal, and K1 should be equal to K signal. So the polarization will be emitted in the same direction as the input field. Phase matching. Right, you can kind of see that the evolution that I kind of wrote here, points 1, 2, 3, 4, are kind of captured also in this trace. Of course, 1 is not captured here explicitly, but you have your dipole acting on your equilibrium state, in this case, dipole acting, that is captured by number 2, then your evolution captured by G, and then final emission is captured by both multiplication with the dipole moment operator and tracing it out. So this sequence of events is kind of intrinsically present in the expression for the correlation function. Make sense? Okay, now with this information, let's write out my correlation function. first I'm going to say my probability of occupying my initial state. I'm starting at 0, 0. Typically, there is some Boltzmann factor. Here I can consider that probability to be 1, but let's say there is mixing of some state. I want to account for that. So I'm going to put that probability to be some 0. Simply a Boltzmann factor telling I have some occupation and finite temperature of the ground state. And now I have to account for number 2, which is acting on the ket to create rho 1, 0, and that is simply captured by multiplying with the dipole moment magnitude. Then I need to write out the time evolution, propagate. This will include a relaxation. Of course, in a phenomenological sense, I could write my g of t to be exponential minus I omega 0 tau minus gamma 0 tau. That's your time evolution. So you can put that explicitly here. And finally, you have to multiply by mu 1, 0 to get this expression, basically taking tricks. That's your correlation function. Basically, write down 0, mu 1, 0 square e over minus I d t. If I look at the diagram, I'm able to construct this. In fact, this looks not that different from what we have estimated. Remember, of course, if I want to calculate total polarization, I need to, the total response function is C minus the complex conjugate, right? That's very important. It's also C star. This is not directly polarization. This is just one of the correlation functions that will enable you to calculate it. Okay, fine. So what is that? So this is C. I know my response function has both C and C star. What is the C star? In the diagram matrix expansion. What is the C star? Now in this case, I'm acting with plus k direction. There's nothing stopping me from acting in minus k direction. Instead of acting on the ket, I could act on the bra. Basically, C star is that. C star corresponds to going to 0, 0, interaction coming from this direction, create 0, 1, and then you will emit light, emit radiation. Could also complicate your life a bit more, saying that there is some finite population also in excited state. So you can kind of write down additional diagrams such as this kind. So you can start with 1, and of course you can emit. So 0, 1, and then this can emit light. Also another Feynman diagram. Linear response has a total of 4 diagrams basically. Okay, so but you can kind of see already the response function has what the form of free induction decay we kind of derived already explicitly present. It's kind of very simple looking, but the important thing is the utility of your double-sided, which is strictly not evident when you are working with, of course, a simple two-level system and just dealing with linear absorption. So let's complicate our life. Let's go to second order response. Okay, is everybody fine?
Just one clarification. Shouldn't the direction of this emission should be like the polarization emitted should be, it's like on the same direction of the field, right? So in the case of you have the complex conjugate, won't it be like emitted on the other side, or it's like
It will always be emitted on that direction because what you are seeing there on the other side is the complex conjugate, right? So if I have plus k like this, it has to come from the other. Does it make sense?
but won't won't it satisfy this phase matching? Like there will be a, you'll have like minus k will become a plus k then.
You're talking about this case,
The top one.
or this one?
Yeah.
What you're saying is this is minus k
Yes.
and this will be plus k.
Yes.
So the in Feynman diagram, the representation of this has nothing to do with the wave vector of the edge. It's just a representation to lower phase. So it is not telling. So just because it's on that side doesn't mean that it's emitting. What you need to do is bookkeep the directions. It's not coming from the Feynman. So only for the interactions, this is plus k minus.
So then,
Not for the emission.
okay, so the k vector of the emitted, the k signal which we are denoting, it's not related to this, it's just the direction which is shown here.
Yeah, exactly. It's not related to the direction of the emission. It is just telling you, okay, it's coming for ensuring that it's completeness. It has nothing to do with the emission. Okay, let's go to second order response. So take second order response. I'll consider slightly complicated stuff. Why not? Consider three levels. So we consider three level. So there is 0, 1, and 2. Remember, second order response are going to have two sets of correlation functions. You will have so-called Q1 which is ket interaction, and you also have Q2 which will be bra-ket interaction. Right? So now let's construct the Feynman diagram here for Q1. Start from 0, 0 again. It has to be a ket interaction. I'm acting like this. This is my ket. This will raise this 1, 0. The second interaction is also ket in this particular correlation function. It will also act in this direction. 2, 0. And then there is no other interactions. So you'll have emission from here. Is this the only interaction that I'll see? Only diagram that I'll have? I will have one more. Several more, but one more at least. Right? Let's write that down. Start with 0, 0. This. Usually your first one is always absorption. Going from the ground state, you cannot have stimulated emission already as your first interaction. So you always going to start on that. And in this particular correlation, you have to go from the ket direction. You cannot go from the product direction. So it has to be the first interaction. Let's say you go to 2 now instead of 1. Why not? Then your second interaction again has to come from your ket direction, which has to be the stimulated emission. Make this. Oh, sorry. And this will emit. A simple way to kind of visualize the energy at which, or the frequency at which the polarization will be emitted is just looking at the last part of your Feynman diagram. You will see that emission is happening from the coherence between the 0 state and the second state. You can already kind of see that my emission is happening at the energy difference between my ground and the second excited state. Whereas the diagram below, it's happening at the energy difference between the ground and the first excited state. You can already kind of intuitively see. That will be the frequency of the polarization, which will be by this coherence, by this particular diagram. Okay, you can kind of also represent it in the ladder diagram. Sometimes it can also give you intuition. I will say it's first interaction is taking you from here to here. Your second interaction is then taking you from here to here. Then you are seeing this. Here's this guy. Going from here to here, the first case. And then you are doing stimulated emission coming down like this, and then creating. If you just examine and look at these two ladder diagrams, does this remind you of anything in nonlinear optics?
2 photon absorption. First one is the 2 photon.
Not 2 photon absorption. Can you think of 2 photon absorption? It's kind of some frequency.
Some frequency and difference frequency.
Now the some frequency generation, bottom is the different frequency. You can rewrite, if you have taken nonlinear optics, you can rewrite all your nonlinear optics using densimetric formulas. Now let's briefly look at the direction of this emission. So this is the first interaction for the top diagram is happening, you're going plus here, so this is plus K1 and this is plus K2, which means your K signal here will be K1 plus K2 for the top diagram. Here you're going plus K1 minus K2, so your K signal will be K1 minus K2. So they will be emitted in 2 different directions. So you can already start seeing how phase matching or phase control enable you to separate out different diagrams. The top diagram, correlation function, will lead to a polarization which will emit signal at K1 plus K2, whereas the bottom one is going to emit at K1 minus K2. Okay? In fact, this will be the trick that we use to access very different excitation pathways. That's the strength of nonlinear spectroscopy. By manipulating the relative wave vectors of each of the field, you can access very specific pathways. and that's very powerful. We will talk about that. Okay, let's, for the sake of completeness, let's also look at Q2. This is a bra-ket interaction. Acting on the bra first. 0, 1, and I need to come with ket here. This could be, what could this be?
1 1.
Could be 1 1
or 2.
could be 2 1. Depends on the frequency I'm using. Okay, so that's a very good point. For now, I'm going to say 2 1, but there is nothing sacrosanct about that. It depends on the frequency what you are using. What will be the direction of emission of signal in this case?
K2 minus
Good. Minus, always for the sake of consistency, say the first interaction first. As you can see, you can write a lot more Feynman diagrams, same way for both cases, depending on different considerations. Now let's just take this diagram, what we have just taken, this number 1, number 2, all this number 3, which is one of the Q2 diagrams. Let's see if you were able to calculate the correlation function. And calculate the correlation function. Correlation function and yes, from Q2. We trace mu tau m 0 now remember what we have already done, it's kind of there. You need to have, as I said, some kind of number associated with the diagram. Remember, one of the rules is -1 power n. What will be that sign that you want to assign for this particular diagram? It's number of interactions on the right side of the diagram. How many interactions exist? 1. So it should be -1. Okay. So that will be -1 whole power 1. Expanding the trace, the kind of implicitly there. So you have your mu 1 2, g 2 1, tau 2, mu 2 0, g 0 1, tau 1, tau 0 0, mu 1 0 star. Did I go too fast on that? Let's dial it down. Let me write it down explicitly. So I'm starting with -1 is there, that's good. I start with rho 0 0. I'm acting from the side of the bra. If I'm acting on the side of the bra, where should the mu go? It should go here. If it goes on that side, it should be a complex conjugate. Okay, then I let it evolve. So G 0 1, 1, G 0 1 corresponds to evolution associated with the 0 1 level system. Then I come with my second typo. right? Second dipole, which is acting on the head side, generating coherence between the ground and the second state, right? So it will be mu to 0. And what I've created is 2-1 coherence with that dipole interaction. And now I need to evolve it. So I have another evolution. Now 2-1. 2-1 of tau 2. And finally, I have to multiply by the dipole moment, take the trace out. Okay, that's the expression. So if I explicitly substitute for my super operators, then you should say minus B0, the occupation factor, mu 0-1, mu 1-2, mu 2-0, three dipole moments, e power minus I omega 0-1 tau 1 minus gamma 0-1 tau 1, that corresponds to my first evolution, multiplied by e power minus I omega 2-1 tau 2 minus gamma 2-1 tau 2, and that's basically your correlation. Now, why did I write down this in this form? Look at this. You can go and plug this in your qubit and calculate this extremely simple. Define your super operators, right? You can define your dipole moment operators, sigma x, for example, and then you should be able to write this down and make qubit calculate this way. But remember, this is not the final response. The final response, you always need to take Q2 minus Q2 star. Okay, that's your observable. The diagram is just a mathematical shorthand. You need to make your final observable with that. Go ahead.
What would the ladder diagram for Q2 look like?
Question. Let's write it down. So your first fraction will be your second interaction acting from here. Sorry, I didn't follow the convention. Interaction this, second interaction this, and then this is your coordinates. When you're acting from the brass side, the convention is dotted line for that. Not convinced?
So normally when you think of it, the first arrow is going from 0 to 1. So you think your state is there, like that state. So
Again, this is density matrix. It's not real.
yeah, so
You're not putting any pop. You're exciting one part of the density matrix. You're raising and lowering different components of the density matrix. So you have to break that thing notion that it's not like a Jablonski diagram where you draw a line up, population is going up. It's not a Jablonski diagram, it's a ladder diagram. It's like it is.
so in the ladder diagram, is there the dotted and the solid arrows represent the brass and the cans?
Yes, dotted line is acting from the brass side, solid line is acting from the cans. Ladder diagrams, frankly, are paid. Segment diagrams are much. Okay, last thing for the class. Third order. Third order is the focus of this course, kind of, right? And we want to be able to calculate third order responses. And third order responses are basically three field interaction. You have, what are the experiments? Take pump probe, 2 pulse photon echo, 3 pulse photon echo, 4-way mixing, coherent anti-stochastic scattering, 2D correlation spectroscopy. All of this are three field interaction. I didn't say 3 pulse interaction, 3 field interaction. You could have, even with 2 pulses, 3 field interactions. Like in pump probe, your pump can generate 2 field interactions at the same time. High intensity. So 3 field interactions are most common in nonlinear spectroscopy, and we need to be able to calculate. For third order, the correlation function, I have already seen that. I have 4 correlation functions. I didn't show you, kind of show you that. Okay, let's take a 2-level system. R1, 2, 3, 4. R1 is always ket interaction. R2 is always bra, bra. R2 always bra, ket. R4 is ket, bra. Okay, good. It's a 3 field interaction. So let's get to business. Work on it together. Verify my diagrams. So 0, act on the ket. Acted on the ket. And I generate 1, 0. I reached 1, 0. If I again excite it, there is no there for it to get excited, so it's not a viable diagram, right? So if I want to act in that direction, it has to be an emission. So this becomes 0, 1. Sorry, 0, 0. So 0. Now I can come back here. This becomes 1, 0. And this is what will emit. Not so good using colors.
So based on what you decide the direction of the arrow.
So excitation, right? So if I'm unstimulated, there are 2 processes. If I'm going ground state, I cannot have stimulated. I need to have an absorption. Now there's only 2-level system, there are only 2 states. I go up, I cannot excite more. I have to come back. That's stimulated.
For 2 level there is only 2 possibilities, and based on the level only one will survive. But for 3 level there
Write down all the diagrams.
Oh.
There'll be 64 diagrams, sometimes 128 diagrams. Okay. Yeah. So that's part of 2D spectroscopy. When you look at 2D spectra, you want to write down all diagrams.
and that is the manifestation of different processes in Chi 3.
That's right. I mean, that will manifest as different processes in Chi 3. Chi 3 is observable. It's because of this you're observing the Chi 3. Right? And by energy considerations and stuff like that, we already kind of eliminate a lot of patterns. You will see when we do, hopefully we'll show an actual experiment. Okay, let's do R2 quickly. Start from 0, 0. Has to be from bra. 0, 1. then a cat. Now I have a population and another bra. I cannot go up more, so I do this. And then I have R3, bra, 0, 1, bra again, back to ground state, and cat. 1, 0. Okay, finally R4. Come from cat this time. 1, 0. Bra. You again go through a population here. Again bra. 1, 0. And that left. Okay. Now write down the wave vector of the emission, where it will be. K1 minus K2 plus K3. This will be minus K1 plus K2 plus K3. This will be minus K1 plus K2 K3. And you have K1 minus K2 plus.
Second one is the minus K3.
Minus K2?
Minus K3.
No, it's plus K3. Emission on the bra side. If it was activating, yeah. Emitting is conjugate. Make sense? So if I should be able to now write down the correlation function. First of all, I know the sign of R2 will be minus 1 square because there are two interactions here. Right? So 1 positive, good. Basically, you have one interaction creating 0, 1 coherence, its time evolution. Another interaction creates a population, okay, and then another interaction which generates another coherence, time evolution, and then decay, right? And then decay means that you multiply with dipole moment at 0, 1 and trace it out. You can see my notes for the final expressions, but I want to write down the expressions for both R2 and R4 because they're kind of very interesting. So we know how to construct that, so I'm not going to go into that. So I'm going to write down for R2 and R4 expressions. R2 B0 10 power 4 exponential minus I omega 10 tau 3 minus tau 1 minus gamma 10 tau 1 plus tau 3 minus gamma 1 is population actually, and R4 0. My notes have derived this, so I can go back and check this. So not need to worry. I tau 0 tau 3 plus tau 1 minus gamma 1 0 tau 1 plus tau 3 tau 1. Also write down the Feynman diagrams for it here, just for the sake of completeness. So R2 1 0 1 R2 this is R4. Okay, everybody is happy with what is written there? If you're not happy, believe me. Trust me. But let's look at what are the differences between these two diagrams. Apart from the fact that the phase matching is different, okay, that I understand. But you see, the final emission is always coming from 1-0 coherence in both of them, right? At the end, the energy of both these signals will be at 1-0. What are the other differences that you see? Either diagrammatically or looking at the expression. So they are identical except for the phase. Phase term. One case it's minus tau 1 and case plus tau. Diagrammatically, what does it mean? It basically means that in R2 at tau 1 you are at 0 1, tau 3 you have inverted that coherence, whereas in R4 at tau 1 you are at 1-0, and even after tau 3 you are in the same coherence. You have not inverted. Here what we call as conjugate, you kind of conjugated the coherence, and that leads to a phase which is acquired phase of we kind of acquire a phase here of e power minus I omega 0 1 tau 1 plus tau 3, whereas here the acquired phase is e power minus I omega 0 1 tau 1 minus tau 3.
No tau 2 dependence.
There can be a tau 2.
But in the phase, are you not accumulating phase during that period?
So in tau 2 you are going through a population. It's just a population decay. And that's identical for both.
Sure, but in addition to the population drop, is there normally not always a phase accumulation that also happens?
Yes, that is there. That is why that gamma term is there.
But there's no omega term?
There is no omega. Population is not population. It's not a coherence. It's population. It's just population. In this case, by decaying into the photon, spontaneous emission. We can discuss this. Now, what I can do now is if I can now plot total phase acquired in time for both these diagrams. Okay. Let's say tau 1, tau 2 is, I'm not propagating, tau 2 is close to 0. I'm not propagating tau 1, tau 2. For my R2, I'm accumulating a phase here till tau 1, that is e power minus I tau 1, and then I'm coming back down. E power, well, this is for R4. 1 tau 3. Whereas for the other one, you're accumulating the same phase in tau 1, but then you're extending the phase on the other direction. Here, you're kind of coming back to the same condition in the case of in this situation. So this is referred to as rephasing, and this is referred to as non-rephasing. What does it mean? What is rephasing and non-rephasing mean? Imagine the situation where there are a bunch of runners. Somebody shoots the gun, they all start running. Not everybody can run at the same pace. Each one is running at different pace. Okay, there are accumulating phase, there's some dissipation going on. After some point in time, I shoot my gun again, and they'll all start running back. Again, their pace has not changed. So when they come back, they will recover all the phase which was lost. They'll all come back in the same time. That is what rephasing is. They'll all start, they'll all go in different direction, and they come back. In the non-rephasing case, they're not coming back, they'll keep going. And they continue to accumulate phase. That's not rephasing. So it so happens the rephasing diagram is very powerful because that gives access to system interactions directly. Because depends on when you shoot your second shot. If you're able to come back exactly to the initial condition, that is a time scale of any kind of rephasing dynamics. So it's very easy to measure or very direct way of measuring rephasing processes. We'll speak more about rephasing and non-rephasing. Not in the next class. Next class I'll start introducing some experiments and start writing out things. But when you start talking about 2D and line shape analysis, we come back to rephasing. Okay?
So in general, the rephasing will not be complete rephasing. Means the phase which is acquired.
It will come back. So of course you need to choose your tau 1, tau 3 appropriately, but at certain given tau 3, depending on system interaction, you will recover the phase.
Okay. But
this gamma outcompetes that one.
Which gamma? Gamma 1 0.
Gamma 1 0 1 tau 1 plus tau 3.
Well, it's not that you're recovering coherence, you're recovering the dynamical phase that you're putting. So it's not that you're recovering the amplitude of the oscillation. I'm not saying that. Think of the phase, it's not the amplitude of the oscillation. We're only talking about the phase. The runners are going to get tired and going to fall down. Their amplitude is going down.
I was talking about the phase only. Means the phase which is acquired in the forward direction.
Yeah.
It may not be equal in general when it comes back.
Well, if you're doing this rephasing experiment, it will be compensated. At some point, it will go to the acquired phase will come back.
Okay.
That's what I'm saying. It will come back. We'll see more examples. So keep that thought. We'll see more examples. Okay, today has been a bit long class, but we have covered a lot of ground, right? The important takeaway is go and think about the Feynman diagrams, how to write the correlation functions, and how do you get impulse response functions from correlation. So once you write the Feynman diagrams, you get the response functions. Once you get the response functions, then you have the polarization, you have the response that you're going to experimentally measure. Okay? All right. There's a bit of sophistication that can be done. Here we have phenomenological gammas here, but one could actually put that in Hamiltonian explicitly using some Lindblad dynamics and make it not phenomenological but based on some specific process. We'll try to see one example of that using Anderson-Cooper line shape theory, hopefully. But the framework is given. Okay. All right. Thank you. Thank you for